Okay, great. Well, thank you very much for having me. I wish I could be at IPAM in person. It's one of my favorite places to visit, but here we are. My background is actually in particle physics, and I have not really done anything in combinatorial optimization until fairly recently, or at least not knowingly. I put it that way. So I'm going to be telling you about some work that we've been doing recently that was motivated by a particle physics context, but includes some touches base with deep learning and combinatorial optimization. So I'd also like to start with the sort of workshop overview, which is always good guidance, I think. So, I think everyone is aware of how deep learning has had impact on, computer vision and natural language processing. I've been, active in trying to use deep learning in the context of the physical sciences. Particle physics and other areas. So again, you see some of the text from the workshop about, the promise of deep learning basically is providing some sort of approximate algorithms that can maybe scale very well and maybe be more general purpose, but then also ending with the idea of there maybe being some synergies between deep learning and some kind of traditional combinatorial optimization algorithms. So my talk will actually, a lot of the meat of it is going to be, what I would consider looks like a probably more classical approach, and I'll hint at how it can be combined with deep learning approaches, and hopefully kind of hit on this last point. There's the traveling salesman problem, and then there's the traveling scientist problem, which is kind of my particular journey in these topics. Several years ago, I was working primarily on Higgs boson physics. There, I was involved with a lot of classical statistics. There, we also have, the predictions are usually encoded in the form of simulators, so that hits on the areas of likelihood-free inference, which recently we've been using deep learning for that quite a bit. There's searching for physics beyond the standard model, where sometimes you work with these objects called jets, which I'll describe in just a minute. And when I first started combining deep learning with that kind of jet physics, I went in this unexpected direction of the connections with natural language processing. So we were using sort of like what we just heard before, techniques that were used in natural language processing being applied to traveling salesman problem. We were using it for this jet physics problem. And there I've gotten involved in just kind of all sorts of different things that have to do with sort of structured data like you see in physics. So data that might look like sets or trees or graphs. And so there's been work with graph neural networks and these other kinds of topics. And recently I was able to make a kind of connection between some of these jet physics problems and combinatorial optimization, and that's what I'm going to be talking about today. Okay, so let me give you a little bit of physics context just so you can see where the motivation is coming from. This is an event display of one of the collisions of the Large Hadron Collider and the Atlas experiment. This detector is about the size of a building. It's about 6 stories tall or something and 11 stories long. And these lines here are particles that are flying into the detector. And sometimes, well, essentially every collision, you get a spray of particles that are kind of collimated or beamed together. Like all these particles are kind of beamed in one area, and that collection of particles we call a jet. So this collision has 2 jets in them, and they're basically back to back from each other. And so this is one of the things that we study all the time, because essentially every collision has several of these in them. And we have a generative model that, from the physicist's point of view, of how these things come to be. So this red is a so-called Feynman diagram that describes particles inside of a proton, like quarks and gluons, scattering off of each other. And this is described by quantum field theory. And we have equations for this, and you can actually write them down on a pencil and paper and use this to try to predict what the scatterings would look like. But this is not the end of the story. Those particles radiate more and more particles called gluons. Those are the blue curly lines, and they radiate more gluons, et cetera, and something that's called a shower. And this we really have to model computationally. You can't really do that on a pencil and paper anymore, because you have this sort of Markov evolution of the showering process, which looks kind of like a tree. Basically, it's binary splittings, so it looks like a binary tree. And then there's some other processes that I won't bother describing. And then these dark green blobs are the stable particles that go flying into the detector. So the challenge here is that our understanding of the process involves this tree-like splitting process, which we don't observe. So that's a latent process. And what we do observe are just the leaves of the tree, which are these stable particles. And those are the things that hit our detector that we call a jet. Okay, so that's the basic setting. We observe the leaves, and then in the process of analyzing the data, one very common task that we would like to do is essentially invert this process. We would like to be able to try to reconstruct the unobserved latent tree Z from the observed particles X, the leaves of the tree. And so in this way, the hierarchical clustering can be seen as trying to invert the generative process. And the standard techniques that are used in the community are a kind of bottom-up, greedy or agglomerative hierarchical clustering algorithm, sometimes called HACK. And there you need to provide a similarity measure that says, okay, which two things should you cluster together? And that is not some off-the-shelf quantity. That's something that's motivated by our underlying physics knowledge, like quantum chromodynamics and special relativity and things like that. So we have a well-motivated heuristic, the similarity measure that tells you how to cluster, and then we just run this agglomerative clustering algorithm. And here are some of the papers that have established some of the main techniques here, and you just see that they're cited thousands and thousands of times. So these are used a lot in the field. Now, this is usually kind of an intermediate task, and there are many downstream tasks that happen after you do this so-called jet clustering. If there was an oracle that could say, okay, for this particular collision, this was the tree that gave rise to those particles, many of the downstream tasks would be essentially trivial, or at least like essentially the optimal solution for many of those like downstream, say, classification tasks would essentially be trivial if we knew the correct tree. But you're never going to know the right tree because there can be several trees that are consistent with the leaves. And so we really need to think of this in some probabilistic way. But usually we don't really do that. We just have like a point estimate. We run some deterministic algorithm. It gives us a tree. We just take it at face value, like it is the ground truth tree. And then we give it to some downstream algorithms that process it. And so we need to characterize the deficiencies in these algorithms and for their impact on downstream tasks. Okay, and that's some more work, and I'm not going to talk about any of the downstream tasks here. But I will say that deep learning has been used in this context successfully. And one of the things that's nice about it is that it kind of removes the need to think about this intermediate tree-like structure at all. You really work with the leaves, and you just go directly to try and solve that task. Sometimes the neural networks there are like convolutional neural networks or graph convolutional neural networks. There's been a lot of exciting work about, trying to think about the different structures that are there, like algorithms that go from sets to graphs and things like that. And I've been involved in some work that tries to be sort of a hybrid of these two. For instance, we've used recursive neural networks where the agglomerative clustering algorithm is embedded together with the neural network so that it actually assembles the architecture of the neural network on the fly. And those algorithms work pretty well. They're very data efficient. They have some advantages associated to them. And so I've been interested recently in trying to think about how to improve them and to try to take into account the fact that this tree needs to be treated probabilistically, because you don't, it's really a probabilistic thing. There is no, real right answer here. So how can I bring together deep learning types of techniques together with this probabilistic treatment of the latent process? So to do that, we need to now kind of frame this in statistical terms. So we need a forward model, most of the forward models we have are coded up in some algorithms that physicists have done that are not very easy to work with. But in principle, what they look like is essentially a kind of Markov evolution, where you basically follow one of these particles and it splits, and every split is independent from each other. And the likelihood for the entire tree is essentially just a product over each of the splittings. So you have a sort of the probability of the left and right child given the parent, and then some other parameters that describe the physics model. Okay, so with that in mind, there's a joint likelihood for both the leaves and the latent process, given the parameters theta. You could talk about like a maximum likelihood history. You could marginalize over all of the possible trees. So that's integrating out Z, which is something that would be nice to do, but it's going to be difficult because there are a lot of trees. You can talk about the maximum likelihood of the parameter theta or a posterior distribution on theta. And the ability to do inference on theta would be something like a new capability for the field. So that if we could do that would be great. So to try to facilitate research on this, my postdoc, Sebastian Macaluso, has coded up a simplified version of this forward model. And it's written in Pyro. It has an interface to things like OpenAI Gym and stuff like that. So this allows us to do research, using things like probabilistic programming, differentiable programming, dynamic programming, variational inference, etc. And this simplified model, it's quite simple. Here's the algorithm for it. The equations are quite simple. And it has the essential physics ingredients. It has energy and momentum conservation, and it has the kind of underlying physics of the evolution, which is sometimes referred to as ultra-Parisi evolution, but whatever, that's the physics content. Okay, so with this probabilistic view in mind, then we would like to kind of go back and revisit agglomerative clustering and what we normally do. So this similarity heuristic that we typically use, which involves the momentum of the two particles that you're considering to cluster and essentially an opening angle between them that's written in a relativistic form, that's the typical similarity heuristic. And if we compare that to the generative model for the entire jet, it's also decomposed into individual pairs. And so as long as this similarity heuristic is kind of monotonic with the likelihood for each one of these, what's going on at the splitting at each node, then we can think of the agglomerative clustering as a greedy algorithm for trying to find the maximum likelihood or match estimate tree. Okay, and so that's kind of nice because we can just rethink about the classical algorithms as trying to find a maximum likelihood or a maximum a posteriori tree given the leaves. And that immediately suggests that maybe we can do better than greedy algorithms with something like beam search or some other search algorithm. Now, the immediate problem that you have is that there's just a ridiculous number of trees. The number of binary trees on unordered leaves grows like 2 to the n minus 3 double factorial. Here's a plot of it. So when n is, even 11 leaves has about 600 million trees. And by the time you get to say 150 leaves, which is a large jet, but it could happen, there's something like 10 to the 300 possible trees. So fortunately, my postdoc was talking about some of the work that we were doing and connected with Andrew McCollum's group at UMass and Nicholas Monath and Craig Greenberg. And the three of them have been doing a lot of the work that I'm going to be showing. So the first thing I'm going to introduce is this trellis data structure. Basically, so first I'll say that what I'm going to talk about next is going to consider the special case of where the cost function that we're assigning to a particular clustering decomposes into basically products over functions of the siblings or like individual splittings. So it has this product over each of the pairs like that. And we have some kind of energy-based model, which if you want, you can try to normalize with a partition function, which is going to be very difficult to calculate because there's a huge number of possible hierarchies. But this model includes the physics problem that we have, a cost function that's used in cancer genomics quite a bit, and also like the Dasgupta cost for people that study some of these hierarchical clustering algorithms. Okay, so what we're going to do is we're going to create this data structure called a trellis. And the trellis is you're going to start with, like, for instance, a tree over these leaves labeled A, B, C, and D. And we're going to think of the power set of those elements. And then and those, so here are, all the different, subsets of those elements. And those are going to be the nodes of this thing that we call the trellis. And what you can do is you can traverse from kind of top to bottom here. And every time you pick one, that's like picking the left child. And then there's an implied right child, which is the complement of that set. And then you kind of recursively go down that process until you terminate at the bottom, and that will encode a particular tree. And so the number of elements in the trellis is large. It's like the power set, but it's super exponentially smaller than the number of trees. So compared to explicitly enumerating all the trees, it's a big win, even though it's still exponential. But what's nice about this trellis is that you can attach data to these nodes. And in particular, you can, if you think of one of those nodes as V, it's one of the subsets, then there's a partition function for all of the trees for that subset. And for instance, the map clustering or the most likely tree for that subset of elements. And then you kind of recursively go down until you get to very small trees where that's doable. And this admits a dynamic programming algorithm for basically navigating that trellis, and it allows you to efficiently calculate the exact partition function for all of the possible trees, and also allows you to find the exact map or maximum likelihood tree. And so here you just kind of see how the full partition function organizes itself into the different nodes that sit on the trellis. And so this trellis, it just ends up being a very kind of convenient data structure for these memoized values. And then that paired with the dynamic programming algorithm allows you to do some nice stuff. Okay, so the problem, of course, is that this is still growing exponentially, but there's a natural sparse version where you just basically, if you work with a sparse trellis, you end up with an approximate algorithm, and for either the map or the partition function. And the way that you do it is you simply just remove nodes from the full trellis. There's a consistency condition that you need to satisfy that's fairly easy. And there's two ways of building one of these sparse trellis. One is to have a source of trees. So for instance, a ground truth simulator that's producing a bunch of trees, or you run something like beam search and that gives you a bunch of trees. So you have some source of trees and you basically fill this trellis and you just keep the nodes in the trellis that have been hit by some sample of trees. Or you kind of go from top to bottom and you just consider some subset of the elements and you just kind of randomly sample through some technique. So this plot shows this as a function of the sparsity of the trellis, where over here on the right, 1 is like the full trellis, and on the left means you have a very sparse trellis. The maximum likelihood tree that's found, and at the top is the exact using the full trellis. And you see that as the sparsity, as you have more of the trellis, you approach the exact answer, while for instance, the greedy and the beam search algorithm are down here. So there's some trade-off there. And there are also different ways to build this sparse trellis, and the performance will depend on kind of how you seed the sparse trellis. So that's one is with beam search here, and another is using trees from a ground truth simulator. Okay. Interestingly, the beam search does better than the ground truth simulator, but okay. So now I'd like to just kind of connect this to some sampling and marginalization and variational inference points. So the point here is that these partition function numbers that you store at every node in the trellis, you can think of them as parameterizing a distribution, a probability distribution over the discrete space of trees. Okay, so there's a kind of an exponentially large number of numbers, but it's much smaller than the number of trees. And once you specify all those numbers, you've exactly specified a distribution over trees. And you can think of that in various ways. For instance, if you have a bunch of trees, you can think of them as essentially a histogram. Like you just each tree is a particular transversal through the trellis. And so you would just increment those numbers by 1, do that a bunch of times, and you would just have an empirical estimate for these partition functions. So you can essentially histogram trees, or you can just set their values to whatever numbers you want, and that's some distribution. And so you can, for instance, fit, if you actually have samples, you could fit that with maximum likelihood. And you can turn it around and you can think of it as a sampling procedure, right? So if you start at the top and you know the partition function of the next level, you can essentially just run a softmax, and that gives you a categorical distribution over the first splitting. And then you go to the next level and you have a new categorical distribution, and it mirrors essentially the generative process that we have in physics. So and this is an exact sampling procedure, and there's no like accept, reject, or anything. That every time you sample, you get a tree. And so this just shows in green the exact probabilities for all of the different possible trees over, I forget how many elements are here. The horizontal axis is the likelihood associated, or the cost associated with each of those trees. And then the black dots are the samples that we get, and it just shows that the samples match the exact numbers very closely. And so we have this efficient sampling algorithm, which is nice. And so when you put these, these two ideas together, you can do some kind of nice things. So for instance, as I mentioned before, if you had a sample of trees, you can do maximum likelihood, fit to that distribution, or you could reparameterize this thing that's, can cover all possible, distributions over trees, and think about, parameterize it, for instance, with a neural network or something like that, and then find the maximum likelihood within that class. Or you could try to do something like learn an amortized posterior, for instance, with a neural network, where you give the leaves as an input, and the neural network has some parameters phi that encode the partition function information, and then that gives you a distribution over trees, and then you can think of that as essentially a variational autoencoder, and together with the efficient sampling algorithm would allow you to do variational inference over these discrete tree-like structured latent spaces. Okay, so that was the first little bit. Last few minutes, I'm going to talk about connecting this with A-star search and reinforcement learning. So this is preliminary work by essentially the same authors that I mentioned before. So what we did here was we used this trellis algorithm and combined it with A-star search. So we're trying to go through the frontier of all possible trees, but it's very large. So the state space is enormous. So we use the trellis both to represent the state space and the frontier of possibilities that A-star search should be considering. And so, yeah, so this is, and then the priority queue that you would have in A-star search is now not just one single queue, it's kind of distributed over the trellis itself. Okay, so it had the priority queue or the frontier is distributed over the trellis. And this right plot shows kind of the decoding the trellis to kind of try out one of the particular possible solutions in your priority queue. And then you can pair this together with a heuristic to try to have efficient search like you do in A-star. And you can, the nice thing here is you can also limit the size of these queues or just the number of steps that A-star considers. And then you end up with an approximate A-star search, but it has controlled computational complexity and allows us to scale these algorithms to many elements. So here's some examples on the left. This is the physics simulator. So here we can run the exact algorithm to about 15 elements. This A-star search allows us to go a little bit further than we could with the trellis on its own. And then beyond that, we only have approximate algorithms, but here you see it scaling to something like 150 elements. And over here for a non-physics example, scaling to about 500 elements. So this is something like 10 to the 1,000 trees that are being explored. And again, this is with fixed computational costs. And we're comparing the cost relative to greedy and beam search algorithms. And you see there's quite a large gap here. So we were able to improve over beam search significantly. And these are just plots showing that, okay, here we were also using more compute than beam search or greedy, but at least it's fixed. So you could adjust these numbers to bring it down and try to do various types of comparisons. But these are sort of recent results that we have. And then I'll spend my last couple of minutes just mentioning some of the work that we've done connecting to reinforcement learning and Markov decision processes. So we did consider the same hierarchical clustering as a Markov decision process, and we sort of had a reward that was connected to the likelihood of the different trees that are being that are like the target, the kind of end state of the rollout of some policy. We interfaced this to OpenAI Gym and considered a few different reinforcement learning algorithms. In particular, we tried Monte Carlo tree search and imitation learning procedure, and compared it to greedy and beam search baselines. And you see that this is a comparison this shows the likelihood compared to greedy and beam search. And you see that you'll see on this right plot, for instance, compared to greedy. And so we definitely see improvements compared to greedy and beam search. The dotted line is the exact maximum likelihood tree based on the trellis in the range where we can compute it exactly. I'll say that this was after a fair amount of futzing. Like the reinforcement learning algorithms did not just work. We had to think a fair amount about how we represented the state space and do a few different things before we got kind of anything reasonable. But after some work, we got something reasonable. But we have not yet compared this to, for instance, the A-star search algorithm, because they were done kind of by different groups, but that's on the to-do list. So I'll end there and say that hierarchical clustering is clearly a very common task. It's something that appears in particle physics, though it's not usually called that. And I think this view of thinking of hierarchical clustering as trying to invert some generative process is very nice, because it brings together lots of things that I'm interested in, like mechanistic models, variational inference, deep learning, and combinatorial optimization. This trellis data structure, I think, is pretty cool. That together with dynamic programming, while it looks like a kind of traditional algorithm, you can think of the trellis as representing a parameterized distribution over all these hierarchies. We can differentiate, for instance, if we run the dynamic program, we can differentiate the solutions, the map, and the partition function with respect to those parameters. We can also reparameterize it and do something like this variational inference approach. And I think these ideas could be probably pretty useful for reinforcement learning or model-based planning, but it's really kind of early days. So with that, thank you very much.